Hi, I'm Brenna Quirk. I'm an online course developer here at InterSystems. Today I'm talking to one of our sales engineers, Elijah Cotterell, and he's going to show us a demonstration of a basic RAG application. So Elijah, do you want to start by giving us just a quick overview of the setup of the development environment that we have here?
Yeah, so we're building this application in Visual Studio Code, which is just a great IDE for sort of Python development or any sort of multi-language development. And just sort of going over some of the dependencies that we've got here for building the RAG application, there are really sort of three main things that we want to think about. Firstly, we want to think about how we're actually going to orchestrate any activity with the language model. So that could be anything from designing prompts to working out memory to actually integrating with the language model itself. The second thing we need to think about is how we access the language model, or which model we want to use. And typically the third thing we want to think about is the kind of storage that we want to access to actually to make use of RAG. So one of the key components of RAG is that you have your own data. How do we access that data? Where is it stored? Is it stored in a raw format, or is it stored as a vector? These are all things that we just sort of need to consider before we get too deep into the actual code. And in fact, the first thing I want to quickly show as an overview of what a RAG application might look like is, again, we've got these sort of 3 or 4 components here. On the far left-hand side, you've got the user, who is typically interacting through some kind of interface like a chatbot. And there are a lot of ways that we can build these natively in Python. So I'm a terrible front-end developer. I really don't have much skill there at all. But using several Python libraries, we can actually build a really good front-end very quickly. And then we've got LangChain in the center, which is sort of our orchestration layer. So this is where we will handle the information pulled directly from our database, the information we retrieve from the language model. It's sort of a centralized way to manage all of that sort of structure. Right. And then again, we've got our actual vector store at the bottom of this diagram as well. So typically we will store data as a vector because it's a great way to embed text or images in a numerical format, which is then really important for making comparisons. You know, how do you judge whether 2 sentences are similar? Well, you want to do it mathematically. And then finally, we've got the language model itself right at the top. So in this case, we'll be interfacing with one of the OpenAI models. But again, there's a lot of flexibility here. If you want to use open source models, that's absolutely fine. There are different providers as well.
Great. So you mentioned that vectors are useful for doing searches, finding similar pieces of data. How does your data actually become a vector? What's that process?
That's a great question. So I've got an example here, which I've called data loader. And part of what we're doing here is there are a lot of open source data sets available online. So if we look at Hugging Face, for example, so over here, for example, we've got a data set provided by Stanford, their natural language processing research group. And what they have here is a long list of effectively article components from different sources, as well as questions and answers about this data. So if we take a look over here, this data is about the Vatican Library, and it's got several questions with answers on it. So, you know, this is one way you might retrieve data, particularly if you want to experiment with language models. Typically, you'll have your own data, but we'll just be using this as an example. And it's particularly useful having questions and answers because we can try and validate some of the responses that the language model is providing. Mm-hmm. So we can impose sort of a structure on how it's going to return information if we want.
Right. That makes sense.
And Hugging Face is great because it has its own Python libraries. So over here, for example, we are using the datasets library, which means that we can retrieve data directly from Hugging Face. We just provide the ID of the repository, and then we run this load dataset command. So it's super simple. And now we can actually interact with it natively. You can use sort of typical NumPy packages to interact with this if you want. And the second component is deciding how you want to store this data. So in this case, we're actually going to create a couple of tables in a vector database. But again, you can instantiate these databases in a lot of different ways. If you're using Chroma, for example, you may instantiate it directly from LangChain. But yeah, different data stores have different mechanisms for creating this storage. But really what we're doing here is just creating a couple of tables. One of them is going to store the actual stories, and the other is going to store all of the questions and answers relevant to it. So we're going to break down that data into more of a row-based format. In fact, if I just quickly load this, so it's going to download the dataset locally. There we go. And then these tables have already been created, so I don't need to put them again. And then the next thing is, well, how do we convert the text into an actual vector, which is exactly what you asked, right? So again, we can use Hugging Face for this. They have a lot of open models available, which are typically sort of text embedding models that we'd want to use for this, since this is all text data, but there are different models for different purposes. In this case, I'm pulling one of these models over here. This has just particularly good results for this data set. You can experiment with different models. There are like rankings available as well. But when I run this, what it's going to do is it's actually going to cache the model locally. You can specify where you want it to live. And to then actually begin embedding this data, we simply provide what we need to the embedding model. In fact, here's an example of some of the data that's been downloaded. You can just sort of break it down like this. These are 10 of the articles. And then if we take a look at this code over here, this section here is really all we have to do to embed any particular part. So in this case, I want to embed the actual questions rather than the stories themselves, because I'm trying to design sort of like a frequently answered question chatbot. So my idea is, if we already have a question and an answer specified somewhere, and we've got, I think, 100,000 of them in this data set, we want to see if the user's question matches any of these first. Right. And if it does, then we can provide them with extra detail. But the benefit of this is we can try and make sure that the questions they're asking aren't too far from something we've already validated. Mm-hmm. If they start asking random stuff that we have no record of, then it's difficult to validate the accuracy of that response.
Right.
So in this case, because we've got these pre-existing questions and answers, it actually gives us a lot of sort of flexibility to really design something with that in mind. So that's what this encode function is doing here. So it's just acting on our model, which we've already loaded. And then what we can do is we can store these directly in our vector database. So in this case, we're actually using SQL queries to insert the vectors directly to the database. But again, depending on the database, there'll be different ways of interacting with them. I'm not going to run this because there are about 100,000 of them, and it will take tens of minutes to complete that. It's already been loaded in there, so you can take my word for it. But yeah, that's sort of a high level, not a high level, that's a sort of very simple case of downloading some data, splitting it up how you need, creating embeddings, and then storing it somewhere to be retrieved later.
Okay.
So what I'll now show quickly is, how do we actually retrieve this data and do something interesting with it?
Mm-hmm.
Currently, it's just sitting in a database. It's just a large number of embeddings. And so what we've got here is actually an application. Now, there are a few components here, so we don't need to look at all of it. But what this is the actual chatbot that we can use to retrieve some of this information. So we're using something called Streamlit, which is a Python package designed for sort of machine learning interfaces. So Streamlit itself isn't a machine learning model. It's not really an orchestration tool, but it's a very well-designed front end to interact with. So you can actually place Streamlit right in front of LangChain, for example. And what we're doing here is just specifying some features of the UI itself. So in this case, we're just defining a header. We're going to choose some colors for the settings, and then we may want to choose different embedding models. So we'll actually be using this embedding model, but you may want to load multiple models, and then you can switch between them based on their individual performance or based on the particular questions being passed to it. And again, language model, we will be using GPT 3.5, but again, you may have different models available, including local models.
So for that embedding model, that is what would be used to embed the question that is sent in?
Exactly.
Okay.
And that's actually a really important point, because you want your embedding for the question to typically match the embedding in the database.
Right.
Because two different embedding models can create completely different vectors. One thing to consider is actually the dimensions of the vector. So this model, for example, all the vectors it creates have 768 fields. There are models that have 4,000. There are models that have 300. So if your vector dimensions don't match, you won't even be able to run any vector operations on them.
Right.
But even if the dimensions do match, they still will have different features. And down here, well, this is where we design our actual LangChain flow. So within LangChain, you have this concept of a conversation chain. So this allows you to very easily build certain components, like templates, for example, or memory features, into your actual orchestration layer. And this means that when you pass certain queries, it can run through these built-in LangChain integrations, and it sort of abstracts away a lot of the more tedious work you typically have to do to effectively push these prompts around and get the data to where it needs to be. So what we do here when the conversation starts is we actually initiate a new connection to our large language model, and we initiate a new conversation with a new memory. Okay. So this means every user will have a completely different conversation available to them. Mm-hmm. Also, part of Streamlit is the Streamlit app is designed to sort of allow long-running connections as well. So this is sort of well designed for potentially having a chatbot open for a long period of time. And then what we'll also do is we'll just create an instance of our database here that we can then connect to. So this is, these are really the main components here. We have our large language model connection, and we've got our database connection here. And then this logic here really just shows us when a user submits an actual prompt through the UI, here's what we do. We'll first encode the prompt using the same embedding model that we've used previously. And then we'll run this vector search function here. And this is where the concept of vectors really comes into play. So we want to match the prompt with the information in our database. And the best way to do that is by calculating the similarity of the vectors. Mm-hmm. And vector similarity is an interesting topic. There are different ways to calculate that. You can either calculate it by the distance between them, or you can calculate it based on the angle between them, or you can do a few different things. In this case, we'll be doing a cosine similarity, so that is the angle between the vectors. If all of your vectors are normalized, then that's typically the best way to go about it. And what this will do is it will return the most similar vectors in our data store. But again, we're comparing the question of the user to the questions in the database, right, not necessarily the articles themselves. Mm-hmm. I think this is a really interesting part of building RAG applications is it is quite experimental. You may find that embedding certain data works better. You may find that you want to embed several bits of data and then effectively chain certain queries together. But what I'll do is I'll actually just run this application quickly. In fact, I should make sure to enter my virtual environment. And then what I'll do is I'll use this Streamlit command to run the actual application. So this is just an example of an interface that you can build. And again, my front-end skills really are terrible, but this is, because we have these Python abstractions, it's quite simple to set this up. So, hi, I'm a chatbot that can access your vector stores. What would you like to know? Now, we have the benefit of already knowing what this data looks like. So Hugging Face typically enables you to preview some of the data like this. So in this case, the questions are about the Vatican Library. When was the VAT formally opened? That sort of thing. So, just to start off with, let's effectively ask that question. Hi, when was the VAT formally opened? Now, again, the idea here isn't that you would ask questions identical to the ones in the database, but instead it's it can very carefully match the questions. And what we find, this is actually a list of all the documents it retrieved. So these are the actual stories relevant to the questions, not the questions themselves, but we can provide this as additional context to the language model. So these first few things are actually about the Vatican Library. That's a good start. If we go down, these are completely irrelevant. So this is, part of, where this sort of level of experimentation comes in.
Yeah.
You need to work out which results are good, which results are bad. Certain vectors will, be calculated as being similar, even if they're not. It's not really a perfect science. But what we can do is, using several layers of querying and prompting, you can actually filter out a lot of this sort of junk. But in this case, we've got all of these documents, and then the actual language summary itself. This is what the large language model provided in response. So I'll actually just close all of these. Vatican Library, also known as the VAT, was formally established in 1475, and it's got some additional information. So, this just gives you an idea of how RAG actually functions. This is based entirely off of the information that we have in the database, and we've specifically demanded that the language model tells us if it doesn't have that information, it won't give you anything. So we try to avoid hallucinations as much as possible. We don't want it to be using what data it was trained on 3 years ago.
Yeah.
We want it to be using the data that we can provide it.
So essentially, you had that list of articles. Those were sent along with the prompt to the large language model. Yes. And so it's using those as sort of source material to find the answer.
Exactly. And in fact, this is a little bit messy, but, LangChain actually lets you follow the prompt exactly. So here are some example responses that we provided. So these were the questions and the answers that were relevant. And then we've got some sort of cut down versions of the documents themselves. So, and this is effectively the list of articles that we showed in the UI.
Correct.
But all of this data was passed to the language model. And there are lots of different ways to do this, where you pass smaller segments. I like to say that when you're building a RAG application, you can have 15 queries for every prompt you send to the language model. That you don't need to pass everything. You can sort of chunk that down and sort of refine those responses. But in this case, it's worked out fairly well. Absolutely. So what I'll quickly show you is, that this is an example of how you might access the database itself as a query. Typically, what you'll do is what's called a top K nearest neighbor search. Top K means, top 5, top 10, top whatever. There are different ways to do this. What we're doing is actually an exact nearest neighbor search. So we are scanning through every vector we can find and comparing its distance, literally. There are more efficient methods, approximate nearest neighbor searches, where you group vectors into certain clusters and you compare those, so you don't have to do a full table scan. In this case, it's quite well optimized, so the performance isn't terrible. But yes, you would typically choose a top, however many makes sense, and try to limit the number of outputs. But the other thing you can do is, even if you find the top 15, for example, you can then vectorize those and run similarity searches on those without having to pass it to a large language model. So you can still cut down on these number of responses in different ways prior to using a language model. And this is sort of what I mean with trying to use these vector stores very dynamically. They're not just sort of, you don't just leave them there and forget about them. You should use them as much as you can to try and make comparisons between the vectors.
That makes sense. Well, this is really cool. Thank you so much for showing me this application. I can see there's a lot of possibilities where this would come in super handy.
Absolutely. And I think the only thing I'd like to maybe talk about quickly, just at the end, is in terms of large language models that are available, these are open models. So not open source, but open in terms of usage. So typically they'll be under the MIT or sort of Apache license. And, this is where a lot of sort of open source innovation is happening. So a lot of these, you'll find fine-tuned versions of these models available on Hugging Face, for example, for certain use cases. But increasingly, we're finding that having very elaborate methods of prompting these language models gives really interesting results. And in fact, in some cases, having a very well-orchestrated prompt on a fairly generic model gives a better result than a prompt on a fine-tuned model. So it's actually possible that you don't need to invest too heavily in fine-tuning a model on your data when a well-orchestrated RAG application can get a better result.
Right. Yeah, very interesting. And we can share links to all of these as well.
Absolutely.
Below this video. So, all right. Thank you very much, Elijah.
Thanks.